Hello everyone, I am Dr. Naresh Kumar, Assistant Professor in the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to have a discussion on EMF equation of alternator and its derivation and its related problems. So first, EMF equation of transformer means alternator. What is meant by alternator? Which converts from mechanical energy to the electrical energy. That electrical energy is a AC supply. Electrical energy is known as a alternator. So alternator, the working principle is same Faraday's law of electromagnetic induction according to the dynamically induced EMF. So now here, rotating conductor placed in a stationary magnetic field and induced EMF will be developed in the armature conductor, that is in DC generator. But here is a different case. Here armature is stationary and field is rotating. So rotating flux cuts the stationary armature conductor and induced EMF will be developed in the armature conductor, stationary armature conductors. That induced EMF is the AC induced EMF. Here is the alternator constructional diagram. So now here this is the field winding. So field poles. So north pole and south pole, north pole and south pole, and these are the stationary armature conductors. In case of DC generator, magnetic field is stationary, and so the diagram should be like this. Magnets are fixed and conductors are rotating. Here is a different case. Magnetic field is rotating and armature conductors are stationary. Armature is stationary and field poles are rotating, and this is the field winding. Field winding is rotating. Here field winding is excited with a separate source, that is DC supply for this rotor winding. Rotor winding is here field winding and stator winding is the that is armature, and that is this is the output. So three-phase supply is given to three-phase supply is taken out from this. So this is the final diagram. So this is the output and this is the DC. This F and this is the R, Y and B. Now the terms related to this alternator. First, P is the total number of poles. Here 1, 2, 3, 4, and F is the flux per pole. For each pole flux in this area, and N is the speed of the rotor, N value, and next F is the frequency supply, frequency induced in this, the induced EMF in the armature stationary core, and next Z is the total number of conductors in series with per phase, total number of this armature conductors, and T is the total number of coils or turns per phase. These are the terms. Now here same thing. Here E is equal to d phi by dt. That means Faraday's first law. E is direct. Induced EMF will be developed in the transformer. In the alternator conductors, armature conductors. E is directly proportional to the d phi by dt. So here the terms related to here flux. Here conductor is stationary. Each stator conductor cuts the flux. So this is the flux. This flux cuts this stationary conductors. Each stator conductor cuts this flux conductor in one revolution, that is phi into P. Here total number of poles P and flux is phi. So phi into P Webers, and number of revolutions per second. So that means N by 60. So time taker for one revolution dt equals to this one equals to 60 by N. This is d phi this one and this is dt this one, and d phi and dt. If you substitute in this, so this is phi p d phi and dt is 60 by N, this one. So now here, so phi p n divided by 60 here. So now here next case, now E equals to, for Z number of conductors, this is only for one conductor. So phi into P into N by 60. For Z number of conductors on stator equals to phi P N into Z by 60. Now next, here n equals to that n equals to total number of poles, this one 120 f by p. This is synchronous speed of the rotor, that means field poles rotation, that equals to n equals to 120 f by p. This is synchronous speed. So that synchronous speed value is depending on the frequency and poles, so number of poles. If you substitute in this here, so now here if you substitute in this, so 120 f by p, this is the n, 5p and z by 60, n equals to 120 f by p. Now here average EMF per turn equals to 5p 120 f by fz 60 into p, and this one is gets cancelled 2. So 60 122 factor here. Now EMF, average EMF equals to E equals to 2 into 5 into P into F into Z. This one. Now here, this is average EMF per turn. So there is a relation for average and RMS from the form factor. So this one here, number of turns, here number of turns equals to T equals to Z by 2. Two conductors frames the one turn here. So this is the conductor, two conductor, this is one turn. Here Z equals to 2 into T equals to T equals to Z by 2. Now here average EMF equals 4 into 5 into P into F into T. So this is Z equals 2 into 2, this is 4, here T. Now here form factor equals to RMS value by average value into 1 is equals to 1.14. So now here form factor equals to RMS by average, the ratio of RMS value to the average value for sine wave. For here we are getting sine wave. So for sine wave, that sine wave, sinusoidal waveform, RMS form factor equals to 1.1. So that I will explain in the next slide. So clearly I will explain, no problem. Now here this is average value. This is average value. If you convert into the RMS value, so now here RMS equals to 1.11 into our average value. So this value is changes for different waveforms, waveform to waveform, for square wave, triangular wave, sawtooth wave, and different types of waveforms. This value for sine wave, so this value is 1.1. This I will explain in the next slide. And if you multiply these two, so that EMF equals to 4.44 F into P into 5 into P into F into T. Now here, this is the final equation for RMS value, RMS EMF next. So the derivation of form factor for sine wave. Same thing here, this is a sine wave, phi of t, and this is omega t. So 0, this is 0, this is pi, 2 pi, 3 pi, 4 pi. And now this time taken to complete one cycle up to 2 pi is one cycle. Cycle means complete set of positive and negative values. Positive and negative values is known as time cycle. So now here, this is time period, time taken to complete one cycle. First cycle and second cycle 2 pi to 4 pi. This is also t equals to 2 pi. This is equals to 2 pi. And this maximum value of flux is phi m. Here flux value is 0. Now here calculate the average value first. Form factor equals to RMS by average value. First calculate the average value, then calculate the RMS value. Now the ratio of RMS to the average value is known as the form factor. Now here phi of t equals to for sine wave, phi of t equals to phi m sin omega t, this one. And for average value formula 1 by t, this is for symmetrical waveform, 1 by t, t by 2, 0 to t, t by 2, f of t dt. This is for symmetrical waveform. For asymmetrical waveform, f average equals to 0 to 1 by t, 0 to t, f of t dt. This don't use this one. This is symmetrical waveform. So asymmetrical waveforms, so use this formula. For symmetrical waveforms, use this formula. Here, this formula is applicable to this waveform because it is a symmetrical waveform. Here time period equals to t 2 pi, this one. And next, here if you substitute this phi average equals to 1 by phi 0 to pi, this up to pi only you calculate, off alteration only 0 to pi f phi m sin omega t d omega t. Now here the integration of sin omega t is the minus cos omega t from 0 to pi phi m by pi. And now if you substitute in this, so now here you substitute in this phi m by pi minus of cos of pi minus cos of 0, cos of 0. Now this minus of minus 1 phi m by pi. So this is minus 1 2, and this minus 2 into minus 5, that is 2 phi m by pi. This is the average value. So this is 2 phi m by pi for average value of this flux sine wave. Next, RMS value. So this is 0, pi, 2 pi, 3 pi, 4 pi omega t, and next for t, phi of t. And this maximum phi m, this time period is t equals to 2 pi. For phi of t equals to phi m sin omega t, and f average. Come for symmetrical and asymmetrical, same consider full complete cycle. F RMS equals to square root of 1 by t 0 to t f of t square dt. Now here f of t is the phi m sin omega t. F RMS equals to square root of 1 by 2 pi 0 to 2 pi phi m sin omega t square d omega t. Now phi RMS equals square root of phi m square, this one square phi m square by 2 pi 0 to pi sin square theta. Sin square t equals to, you can write this 1 minus cos 2 divided by 2. You can write this one. Now if you integrate this one 1 by 2, and this if you integrate this one 1 by 2 omega t, this is 0 to 2 pi minus 0 to cos omega t sin omega t, the integration, that one 2 omega t by d. Now 0 to 2 pi. Now here sine of 0, pi, 2 pi, 3 pi, 4 pi, multiple of pi, sine of multiple of pi, always 0. So now here 0 and 2 pi, this value is completely 0. Now here if you simplify this, now here this square root of phi m square divided by 2 pi and 2 pi minus 0, 1 by 2. So this value equals to phi m by root 2 only. Now here this form factor equals to RMS value by average value. This is the phi m by root 2 and this is the 2 phi m by pi. If you simplify this, you will get the 1.11. Sine wave, sinusoidal waveform form factor is always 1.11 for any waveform, for voltage waveform, for flux waveform, for current waveform, for any waveform, that value is 1.11. So now this is 4.445 into P into F into N, and the form factor equals to RMS by average value, that equals to 1.11, and this is the average value, this one, and RMS value equals to 4.44 phi into P into F into T, and this is KD into KC, F into phi into T. Now here KD equals to sine of M beta divided by 2 M sine B by 2. KD is the distribution factor, and KC equals to, here M equals to number of slots in the armature stator and number of poles and number of phases, and here beta equals to 180 by N, and N equals to slots per pole. If you know the slots per pole, and you can calculate this beta, and M equals to, and if you know this N, beta and M, then you can calculate the KD, and KD is distribution factor, you can substitute in this. And next KC equals to cos alpha by 2. This is the Kc, coil span factor. Now here problems related to EMF equation of alternator. A three-phase 50 Hz star-connected alternator has 200 conductors per phase and the flux per pole is 0.0654 Webers. And calculate the following induced EMF per phase and EMF between line. So here induced EMF per phase means E phase voltage and line voltage EL. So there is a relation. If you calculate this phase voltages, EL equals to square root of √3 into V phase. This is, if you know the V phase, then E phase, and then you can calculate this line terminal voltage. Line voltage from the phase voltage, you can calculate the line voltage from the three-phase circuits formula. So first E phase formula. So that equals to the given data first here. So now F equals to 50 Hz and Z equals to 200. So from this, the T equals to 2 into Z by 2T, that equals 200 conductors. So 200 by 2, that equals to 100, and flux equals to 0.0654 Webers, and calculate the following EMF, that is E phase you need to calculate. So that this is full featured means this Kc equals to 1. So this here Kc equals to 1 and Kd equals to distribution factor equals 0.86. So now we have all the parameters in the EMF equation. E phase equals to 4.44 Kd, Kc, F, phi and T phase. Now here, so this is the 4.4, this is the Kd equals to this one 0.866, and this full pitch, this is Kc, and frequency is 50 Hz, and this one is the flux, maximum value of flux, and total number of turns here 100 T. Here in the form of conductors, total number of armature conductors, but here we need only number of turns only. Now the EMF per phase is 1248 volts and the line to line voltage. So E phase equals to √3 of EL equals to EL, line voltage equals to phase voltage multiplication this one. Now here 1 per √3 means 1.732 and 1248, that equals to 2162 volts. This one 2162 volts and 1248 volts. Next problem. A three-phase 50 Hz alternator is running at 600 RPM, has 2-layer winding, 12 turns per coil, 4 slots per pole per phase. So this is M, and the coil pitch of 10 slots. Let us find the induced EMF per phase, E phase, and if flux per pole is 0.035, 35 milliwebers. Now here, how you will calculate this one? So solution for this. So first induced EMF formula. So we know this formula E phase equals to this E phase we need to calculate. So this E phase equals to 4.44 into Kd into Kc, distribution factor, and this coil this Kc, and F into phi into T phase, frequency into flux into T phase. Now here, so what are the flux value is given and frequency value is given, total number of conductors. Here how many number of conductors, that uh, from this 12 turns 4 slots. From this you can calculate the turns. You can first KD and KC is the most important, the calculation of KD and KC. So first here KD equals to sine of m beta by 2 m into sine beta by 2. Now here m equals to number of slots per pole for phase, and beta equals to 180 by n equals to number of slots per pole. Now here Kc equals to cos of alpha by 2. So first m equals to number of slots per pole for 4. This one is 4. This is okay. 4 this one. And what about beta? Beta equals to number of 180 by n. This one, this we know is, and n equals number of slots per pole. Now here is the question. There is no n value. They have not mentioned number of poles and number of slots. So poles we can calculate from this one and this one. So n equals to 120 f by p. Now here if you from this you can calculate the poles, and slots we can calculate from this slots. This number of slots per pole means there is a 3 phase. So from this you can calculate the slots. So now here n equals to 120 f by p. So now here from this 600 equals to and 120 f by p. So here p equals to 10 poles, 10 number of poles. So this we have 10 poles. And next, slots. How we will calculate the number of slots? Total number of slots equals to this 4 into this one, this total number of slots, this 4 into, and this poles into, and this 3 phase. Poles are 3 and these phases are 3, and this total number of slots per pole per phase. Now here total number of slots are 120. Here now we have total number of slots 120 and total number of poles are 10. So what about this slots by pole is, that is 12. Now we have 12 n value 180 by 12. So that is beta equals to 15. So now you can easily calculate KD equals to sine m beta by 2 divided by m into sine beta by 2. So here m equals to this 4 and beta equals to 15. This is m and this is beta. And if you simplify this, and that value equals to 0.958. And the calculation of this one, this alpha equals to this total number of turns here 12, and this coils pitch are total 10. So 12 minus 10 into this angle 15, that equals to 30 degrees. Now here Kc equals to 30 by 2 of cos, that equals to 0.966. Now here E phase equals to 4.44. This is the KD and this is the Kc and this is F. This value is flux, and this is the total number of conductor turns equals to 120 into this 4, that equals to 480. That voltage equals to 3451. So directly we know this formula, but here the main task in this problem is KD calculation. KD can be calculated from this formula m beta by 2, and m is given here, but beta equals to 180 by n. N is calculated from n slots by pole. Here poles are calculated from this formula and slots are calculated from this formula. After getting this, you substitute in this, then you will get the beta, and then you will get the KD, and KD, after getting KD you can substitute here. Now next problem is related to same type of problem. A 3-phase 50H star connected salient pole alternator, 216 slots with 5 conductors per slot. All the conductors of each phase are connected in series. The winding is distributed and full pitched. So this Kc and Kd is 1, and the flux per pole is 30 milliwebers. And the alternator runs at 1250 rpm and determine the E phase, this one E phase and this line voltage EL. First you calculate the phase voltage, then you can calculate the EL equals to root 3 into phase voltage, phase induced voltage. Now here the formula is E phase equals to 4.44 kd into kc into f into 5 into this T phase. Now here same last problem, kd equals sine of m beta by 2, that divided by m into sine beta by 2, and next kc equals to cos alpha by 2. Now here beta equals to 180 by n and n equals number of slots per pole, and number of poles can be calculated from 120 f by p. Here number of speed is 250 and this frequency is 50. From this you can calculate the total number of poles, that are 24, and total number of slots equals to, here 216 already they are given, 216. M equals to, here slots are given, M equals, what about M? M is total number of slots per pole and 24 by 3, that value equals to 216 divided by 24 by 3, that equals to 3 only, 24 into 3 and into 3 equals to 216. Now here M equals to 3 and this slot angle, this 2 number of n equals number of slots per pole, that equals 216 by 424, that equals 9, and this angle equals to beta equals to 180 by 9, that equals to 20, and if you substitute in this you will get 0.951. So kd equals sine m beta by 2 and m sine beta by 2. Here this is 3, m equals to, and this beta equals to 20, that equals to 0.959. And next, number of turns. How we will calculate the number of turns? Here this 215 into this one, this is z. Z by 2 is actually this turns equals to z by 2. So z by 2 means 216, total number of slots into 5 conductor per slots, this one is okay, by 2. Here per phase, here 3 number of phases, here this one. So now here 216 into 5 by 2 into 3 equals to 180. So now here substitute in this, E phase equals 4.44 kd into kc into f into 5 into T phase. This kc equals 1 because it is a full pitch winding, and this E phase equals to 4.44 and this is the kd, that equals 0.5959, this is kd, and kc is 1, frequency is 50 hertz, and next this is the flux, this 30 milliwebers, and this 180 is total phase. So now here the EMF is 1150. Now this is line phase voltage. From the phase voltage you can calculate the line voltage, that equals to, here that EL equals to 1.732 into, so EL equals to root 3 into E phase, that equals to root 3 equals 1.732, this is this one, and that equals to 1991 volts line voltage. Next problem. A 4-pole 3-phase star-connected alternator has 12 slots with 24 conductor per slot, and the flux per pole is 0.1 Weber, and calculate the line EMF EL at 50 Hz. Calculate the distribution factor of 36 slot 4-pole single phase single layer winding alternator. Now here E phase equals 4.44 kd into kc into f into 5 into T phase, that equals to this one. Here kd is calculated from this one. Here m equals to 1 So number of slots per pole for phase. So that equals to 12 by 4 into 4 by 3, that equals to 1 only, m equals to, and this slot angle equals to. So here number of m equals to number of slots per poles per phase. Total number of slots 12 and poles are 3 and poles are 4 and this one. So 12 by 4 into 3, that equals to 1. This one m equals. And beta, how we will calculate? So now beta is calculated from, now here beta equals 180 by n. Now this n equals to 3. How you will calculate number of slots per pole? So number of slots 12 by 4, that is, for n equals to 4, that equals to 3. 180 by 3, that is 60. So now if you substitute in this, Kc equals to 180 by 3, Kc alpha by 2, 180 by 3. This is n and this is 0.0866 and this Kd value is 1. Now total number of tons. How many number of tons here? Tons equals to, now here total number of tons 12 slots and to this one 12 into 24 divided by here 3, that equals to 3 into this one 8, this one 96 number of tons. Now this one E phase equals to 4.44 into 0.866 into 1 into 50 into 0.1 into 96, that equals to 1850 volts. I hope all these problems are clear to you. If you still have any doubts, you can comment in the comment section below. I will answer to your queries. Thank you very much to you all.
Like, share and subscribe. Hit the bell icon for more updates.